Let's put a graph in motion to kind of make it show us what's going on as time goes by. Again, we're still looking at the same scenario. We've got the stationary car. Initial horizontal velocity is 0. The car's initial velocity in the horizontal is 0. The person and the ball's initial velocity in the horizontal is 0. So it's not moving side to side. And the person's going to launch the ball straight upward. And then it's going to go slow, slow, slow until it stops, and then it's going to speed up, speed up, speed up until it comes back into the person's hand. Now, an anomaly of trying to animate these things in PowerPoint is that it's going to seem to be going faster as it reaches the top and slower as it reaches the bottom. So I apologize for that. All right, I'm going to put this in motion and try to track the path of the ball as we put this in motion. Well, if you were really focusing on the ball, here we'll put that up there again. If you really focus on the ball and try to not focus on the graph, you'll see that the ball is really traveling straight up and down. But if you try to watch the graph, it will appear that the ball is taking a curved path. Well, was the ball's path curved? No. But again, as we mentioned, time was going by while the ball was going up and coming back down. And so what we've plotted on the x-axis here for projectile motion is time. And so that while the time was going forward, time was passing as the ball was thrown up and came back down. Okay, we need to now consider a separate hypothetical scenario, and it's got different implications. We'll have the same person standing in the huge train car with the glass sides and so forth, and now the train car is in motion. It's on a straight level track, and it's going a constant 20 meters per second. This time the person's not throwing the ball, they're just holding it as the train goes along the track. So you think about what's this going to look like. I'll be thinking about it from the perspective of the person inside the train and from the perspective of the person outside the train. Okay? We'll set this in motion, and now notice I've shown a vector here for the velocity of the train, the person, and the ball, since they're all staying fixed relative to each other. The train, the person, and the ball are all fixed relative to each other. They're all going 20 meters per second to our right. And the initial vertical velocity of the ball is 0. It's not being dropped, it's not being launched, it's being held right there. All right, so here's what this should look like, sort of. All right, I apologize for the kind of catching in the motion of the background. It's not perfect to animate these things in PowerPoint, but you get the sense that the train is moving through the scenery, or if you just reverse the perspective, the scenery is going past the train. It's supposed to be going past it at 20 meters per second. We need to consider, from the perspective of the person in the train, what's the path of the ball? Well, the person in the train's holding the ball at the same height the whole time, not moving relative to the train car, which is not hard to do if the train is going a constant speed, not speeding up, not slowing down, not turning left or right on level track. It's not hard to just hold a constant position. And so this person's holding the ball in the same position. So to the person standing inside the train, the ball is stationary. Now, of course, the person standing beside the track and probably a little ways back, so that they could keep a good view of it as the ball moved along the track. Watching the train go down the track would see the ball moving in a straight line horizontally from left to right as the person went by at 20 meters per second holding that ball. Okay, well let's see what the graphs should look like. Here again, we're looking at vertical position. So in the vertical, what was the displacement of the ball during the time that we're considering? Well, it didn't go up, it didn't go down. So it was just stationary in the vertical. It had its original position, and a quarter second, a half second, 3/4 second, a second, second and a quarter, and so forth. As time went by, the ball just stayed at the same height. So there's no change in position, no displacement of the ball in the vertical while the train was traveling down the track. The horizontal is a different matter here. Now we're looking at the horizontal position of the projectile versus time, and you might say, well, it's not a projectile. Yeah, okay, so it's not a projectile in this case, but the ball is actually moving. Now remember, our y-axis here is supposed to be the dimension in which it's moving as time goes by, according to the way we plot these things. So the ball is moving a fixed amount of distance down the track, about 5 meters for every quarter second, and it keeps on moving 5 meters for every quarter of second that goes by, because it's going 20 meters for every whole second, right? So for every quarter second, it's going 5 meters further down the track, and that gives us a straight line plot. And what's a straight line plot of displacement versus time tell us? Tells us constant velocity, right? So the ball is moving at a constant velocity of 20 meters per second. You could find that from the slope of this, 20 meters per second. That would be the velocity. If you go forward another second, you go up another 20 meters to get the next point. So 20 meters per second would be how fast that ball is moving to the right. So if we set this in motion and let our graph run, well, this isn't going to seem so intuitive, but we need to think about what it represents. Okay, so here we go. Again, now the scenery is going to be going by. Is the ball going up or down? No, it's going to stay fixed and stationary relative to the person and relative to the train car. But you can see, even though its height doesn't change, its forward position is changing more and more and more. And actually, unfortunately, our simulation has to stop because I don't know how to work it any better. But as time went by, if that train car continued at 20 meters per second, these data points should just continue filling in further and further and further at a constant slope of 20 meters for every second. So again, we're doing all this to try to understand how to solve projectile motion problems, and we need to consider a more complex hypothetical scenario now. We've got the same person standing in the huge train car, and the train car is moving at a constant speed of 20 meters per second, just like the last scenario, on a straight level track. This time the person throws the softball up, straight up, and then catches it at the exact height from which she had released it. So it seems we're combining the two things, the two aspects of motion that were represented in our two previous examples. That's what we're doing indeed. So the train car is moving at a constant speed of 20 meters per second. The person inside is fixed relative to the train car, standing still, and is going to throw the ball straight up. And if you think about it, the ball's going to go straight up and come back down into the person's hand, because the ball is moving 20 meters per second, the person's moving 20 meters per second, the train car is moving 20 meters per second. Since it's inside a train car, there's no air resistance or anything from the outside pushing the ball around, so it's not going to move forward or backward relative to the person standing there. So it's going to go to the person inside, it's going to go straight up, come back down, and meanwhile the train will be further down the track. Let's put this in motion and get an idea what that looks like. I just described what should be the view of the path of the ball according to the person on the train. That is, that the ball left her hand, went straight up, and came straight back down into her hand without her having to move her hand sideways or forward or backward. Now, to the person standing beside the track, they're seeing the ball going forward at 20 meters per second while they're seeing it go upward and slow down until it stops and then speed back up in the downward direction because of gravity. So it sees, the person standing beside the track sees both of these happening at the same time.